Welcome everyone to our seminar today. We're introducing Deniz Eroglu from Kadir Has University. Just a background, Deniz received his PhD in theoretical physics from Humboldt University. Humboldt,
German,
yes, in 2016, and has held the postdoctoral positions at University of Sao Paulo, Imperial College, and Northwestern University. And now he's an assistant professor at Kadir Has since 2019.
Yeah, correct. Yeah. And a quick update. So I moved to Imperial College very recently. So now I'm working at math department over there.
That's good. So his research focuses on complex systems, nonlinear dynamics, data-driven modeling of networks, and he currently leads the Network-Oriented Dynamics and Data Science Research Lab, or the NODS Research Lab at the university. So yes, here we are welcoming him and looking forward to the talk.
Thank you very much. So thank you very much. Yes, so I do still hold a permanent position at Kadir Has University. So and then we do have a research group over there working on network-oriented dynamics and try to blend some ideas from data science, put them together, and today I will talk about this kind of research. But recently moved to Imperial College as a Marie Curie Fellow, and then I will be in London for some time for sure. And very good engaging with all of you. Thank you very much for having me. And today, so I will really try to kind of fulfill the name of our research group, Network-Oriented Dynamics and Data Science. The idea is the following. So I've been working on interacting dynamical systems for a while, and the general idea is the following. So we do have some systems, and then normally we maybe understand the individual dynamics very well, but whenever these units are coupled on somehow network structure and so on, understanding the behavior or predicting the critical transitions by applications, I do not know which language you prefer, is getting super challenging. But actually the main problem starts from this perspective. In general, we do observe many things. So we do collect a lot of data, and afterwards we try to make sense of this. And then if we can model this kind of systems, maybe we can predict future critical transitions, and then this might help us to avoid some big catastrophes and so on. So today's lecture talk will be on this, and we have a special system, and then from this special system we can get data. You can just consider all these white points like my nodes. They are each one dynamical system. And then from these points, we can collect the data. These are time series, as you know. And then if you want to understand what is going on at a single point, by looking at only the data coming from this point, might be tricky or might be misleading, because these things are not really driven with only internal dynamics. So not only with intrinsic dynamics. Actually, there is a network behind it, and then these nodes, this data that we collect, also driven by the neighboring nodes, vertices, and so on. Then, if we do such observations, and then the main problem, which is called inverse problem, is how can we learn what is the dynamics of these individual units, and how these guys are connected to each other, what is the graph network, and then also how these guys are talking to each other. This is represented with H, which is a coupling function between the oscillators. So we want to find out, we want to solve this problem, and why this problem is important, maybe we can just show an example application of it first. So if you consider brain consisting of many different parts, and then each part is basically controlling some functions, like audio functions, like right visual things, or motor functions, and so on. And from brain, in brain actually, so if we are understanding each other right now, this is because of some synchronization, so between some critical transitions. Synchronization should be there on brain activity between neurons, but there is also some additional region, which is called rich club, so connecting basically these different functions to each other. We can simplify it in that way. If there is kind of synchronization in rich club, then in this case, then some pathology is done. So which means some type of synchronizations are good, some of them are not okay. And now the goal is then this. If we do have data from brain structure, we can simply abstract the neurons into graphs. So probably many of you working with networks, as we are at Network Institute, right? So, and then neurons can be like represented by nodes. And then in this case, if I say like one wing of my abstract network, like topology structure, controls one of these functions here, like blue and purple, and then in the middle, as you see, so like these red ones belongs to some leaf clusters, and then also into this red one in the middle. So if there is a synchronization between these different parts, and in general message goes through this rich club structure. Very good. So now idea is the following then. If we have data from this point, can we reconstruct the network structure, network dynamics also, like coupling and then isolated dynamics and then everything, and then can we predict when this system will go to transition? So, or we can say this, when the rich club will go to synchronized states. So can we predict this? So this is our research problem. And then mathematically, we can define it with some simple equations. So here, so this is like a discrete way of showing it. We do have states, x, and then equals this fi, which means ith isolated dynamics, f. And then this is coupled with some other guys through a network structure, aij, and h is the coupling function. Here we have a scalar alpha, which is coupling strength. So this is basically how intensively these neurons are talking to each other. So basically talking about this. All right, so as we are talking about neurons, so we can choose neural dynamics. And we know from neuroscientists, in general, neurons are connected to each other with weak coupling, small coupling. And as you see, the spikes, the interval between spikes are also changing, not regular, so not evenly distributed somehow in space. So which means we also have chaotic dynamics. So in this case, if this is the problem, like we have super chaotic dynamics, coupling is super small, then which means due to nature of chaotic systems, there is like an exponential decay, right? So in correlation. So because of that reason, we do not expect actually any correlation between these units. And then if we measure the correlation, as you see, like these are the node indices, like up to 100 nodes. And then here's as well. I'm so sorry. Can I go back? Yeah. And as you see, like everywhere is blue, which means there is no correlation, although they are connected to each other in this graph. So, but this makes sense. Chaotic units, weak coupling, and then we do not expect to see any correlations. And people, they do try some different ways, like instead of linear similarity measure, they can use like mutual information one, or like entropy-based things, or some other machine learning approaches, wavelet analysis, and so on. In this case, there is no possibility to find interaction signs in these neurons because of the setting of the problem, like super chaotic, fully developed chaos, and the coupling is small. All right, and if we believe that, so this is the structure of brain or the dynamics of brain, how can we reconstruct the network structure, and how can we predict when the system or the rich club region will go to synchronization. Okay, so let us start with some heuristics. As you know, brain is a structure and its topology, network, degree distribution follows Pavlov. So which means we do have rare hubs and we have abundance of too many low degree nodes. So due to this scale-free structure. And then if this is the case, and then if you remember the equation a little bit, so the system has internal dynamics F plus some coupling term, and then this coupling term depending on the number of links. And if we have this low degree nodes, their coupling term almost not negligible. So, and then which means we say like these guys are poorly connected, and then they are almost independent in our network structure. If we go to hubs, this red bodies, then here, as you see, we do have many connections. And then as we have many connections, instead of basically considering this part in this discrete summation, maybe we can apply some ergodic theory, and then we can just somehow find out a local mean field. And then as we do not have infinitely many connections, there will be some nice mean plus some fluctuations, because we cannot really integrate it, right? And then if you basically have this heuristics pocket, and then we say we have like hubs, and then these hubs are super well connected to the rest of the network in the order of like n square root of n system size. And then if H is smooth one, and then if C2 is an expanding map, like doubling map and so on, and then in this case we can apply some mean field theorems. And when you do this under these assumptions, our equation becomes into this form, and then which is a super nice reduction. So we although go through only with one slide, it took like about 3 years to solve. This form gives us a lot of power. So here we cannot do much things, but when you go into that, then afterwards, if you think a little bit carefully about the problem, then you see we can split the problem into pieces and then solve every piece one by one. At the end of the day, we can get back to the origin. How we do this? The idea is maybe it's also good to explain what are these things. So this V is, as I told you, the mean field. This H is the coupling function of us. We had it in the model already. And then this nu is a physical measure, Borel measure. I don't know if you ever heard of it. And then it's just somehow explaining the mean interactions on, in general, hubs. Why I say hubs? Because as you see, so this equation became now into like depending on Ki. And then if I add a low degree node, this is very small number, maybe 1, 2, something. And then alpha is also weak due to like this brain structure. Then this part for the low degree nodes is simply negligible. This is the fluctuation part, as we do not have like infinite many interactions on the hubs. So this is the fluctuations, basically the mismatch of this integral and then the discrete summation. So as alpha is small, and then as the fluctuations will be also small in the low degree nodes, then if I can classify which nodes are the low degree nodes, I can simply neglect these parts. And then if I have many of them, taking another average over the function of, or graph of the function, then I get really what is f. And then if I learn f, then what can I do? I can simply move this f towards left of the equation, and then I am left with only the coupling term. So in hub, as this is a dominant term, so this will be very easy to put everything on left and then solve the problem for V, mean field, with some scalar alpha and ki. For this, so you need to do a little bit numerical tricks. You get data, check the graphs, and then probably low degree nodes will show the same functionality because they're abundant. There will be many of them. By checking the similarity between these graphs, then you can just basically classify which one is low degree node, which one is hub. And after this trick, then you start learning the effective coupling V and multiply with the degree of the node I. So this is nice. So if we know this, which means we learn all the KIs, which means we have probability distribution, so degree distribution of the network, which is statistical property of the network. And then this basically helps us to do a lot of predictions. This is good. But apart from that, maybe we can try to approach to real networks. So how can we find it out? Then the idea is the following. So we simply split our time series into deterministic and then fluctuation part. So here we learn what is F, and then we learn what is this effective coupling. And then if we basically put all those deterministic parts away, then we're only left with the fluctuations. Normally, if you do the similarity analysis with correlation, mutual information, whatever, and the reason that we cannot see any functional network because this deterministic system is chaotic and broadband large. And this basically decays the correlation exponentially. But if you learn this and then if you remove it from the original time series, then we will only be with the fluctuations. And if you measure the correlation between fluctuations, then we can get the communities in the beginning we showed. So here is an example. This is cat brain network, so you can find it online. So quite famous graph. So some time ago, in 1993, I guess, yeah. So this Zoom puts a lot of things around, so I cannot see my full screen, sorry. 1993, so I guess that time science was a little bit more brutal, or maybe they were allowed to do whatever they like, and then they kind of, it's a little bit bad, but kind of open the skull, and afterwards start painting like a live cat's brain, and then afterwards trace the color going through. And this simply, as far as I understand, helped them to find out the structure. So this is basically the abstract way of this brutal process, and likely they do not do it anymore. And we do have this clusters. These clusters found by the neuroscientists, not by us. But what we can do, we can put our dynamics on these nodes, do the simulations, and afterwards we can simply proceed the algorithm that I showed you a second ago, and then maybe we can try to find out the fluctuations. And then if we find the fluctuations, then afterwards if we find the fluctuations, then we can simply measure the correlation between these fluctuations with respect to node y, pairwise between nodes. Then if we do this, then we get such a correlation. So normally in the beginning, so we had like entire time series, and then when we measured the correlation, we didn't see anything. Everywhere were blue, if you remember. And then now you see we have some red, nice colors hatched on our matrix. And then these are simply saying us how these guys are connected to each other, and then this shows really the cluster cell. So here is like the visual part, this is auditory, motor functions, frontal limbic, and so on. And then if I go and then apply some soft threshold thing, and then just basically remove, binarize the matrix by a threshold, then I can get such a network. And then if I do, if I basically find the communities, if I apply some community detection algorithm onto this graph structure, and then as you see, I find very similar network to the original one. And then the visual ones is like this, U1s and so on, so on. As you see, this is not 100% correct, but good enough to at least find out this rich collab members. So there is also another algorithm to find rich collabs. So we applied it here. So we found previously these ones on the original network. And then in the second network, which is the reconstructed effective network basically. And then we do find more or less whole rich collab members with 2 additional mistakes. But this does not really stop us to do the prediction of these critical transitions that I will show you in a second. So with this is quite actually nasty type of coupling function and so on. In coupling function, so we use electrochemical coupling scheme of these neurons, which is very complicated equation. As you see, we are not interested in finding exact age here, so coupling function, and then we only try to find the mean field of it. Because of that reason, we had no problem, but we could only learn exact statistical property of the network and communities and a rough network. But as you see, there are a lot of mismatches in the real network. So here we have like many connections, here we have super less, and so on. Why it is happening? Because of probably our threshold or some other reasons, and of course like limited network size, limited connections, mean field theorem, ergodic theory works this much. This is a great result. Yeah, in these conditions, bad conditions. But if we somehow generalize the problem, but also put a little bit more, if we change our assumptions a little bit in this H coupling function, so if it is like linear and a diffusive coupling, like electric coupling of neurons, and in this case, what we can do is the following. Now, network is not a binary network, which is like weighted network. In this weighted graph, so our reduction theorem works perfectly. And if H is in that form, as I told you, and then plus if I add some dynamic noise in my system, in this generalized form, I can apply this reduction theorem, and due to the assumption on H, I can write my equation in this very compact Kronecker form, which is basically just put together all these vectors, fields, and so on. So everything into this equation, which basically comes with like Kronecker product here, but it's nice and compact. And then if we get into this form, then we can use our reduction theorem again, and instead of learning only statistical property, what we can do is the following. We just basically put everything again left, and then we are left with somehow this structure, this coupling part, which can be written as y equals gx. So x is our state, y is basically our original state minus the previous state's function. So this actually makes a lot of sense, because this, if there is no coupling, this should be 0, right? F of x should be x of t plus 1. And then due to this coupling term, so we do have some fluctuations again, it's y, and then this can be solvable with this linear equation, y equals gx. And when we do this, when we solve the linear equation, then we get the following structure. Here, the main issue is solve this problem. If you want to solve this linear equation, of course, there is no solution. So in general, number of data is less, and then you need to put here like some forms and so on due to your network size. And as there is no unique solution, then you need to relax the problem into some vicinity of the exact solution. So you are just basically trying to approximate your result. So because of that reason, you need to somehow penalize your regression algorithm, and this can be done with different ways. Here we used basis per set. First we took it, and then we just basically do the regression with L1 norm. And but as there is no unique solution, so it will not give a perfect result. And what we do instead of basically try to equalize this thing to zero, so you just basically find the solution around the neighborhood of it. And then after applying this basis per set, so then we got the exact network perfectly. Just whatever we needed to find, we can find exactly under these assumptions, these conditions. And then here is the noise parameter that we have added. So these numbers seem small, but they're actually quite big because the coupling is also super weak. So they are comparable numbers. And then up to a certain point, like noise intensity about like 0.003, so we can get really perfect reconstruction. And if for different network sizes, here is like false negatives, here is false positives, and which means both of them error, so they should be very small. And up to a certain noise level, if we have this better conditions than the first part, and then we can really reconstruct entire network with the reduction theory. All right, so and as promised, so if we have such a system, and then if we set our coupling strength 0.3-ish, and then in this case we can go and then we can collect some data from the system, then afterwards we can forget about everything and then do the prediction from the reconstructed network. And then if we do this, then we really learn what is critical alpha, which is 0.42 for us. And as we had some mistakes, because of that reason, we do have some standard deviation in the prediction. So, and we expect if we simulate this system for some time, analytically we can show that the system will bifurcate around this point. And then you see, so we have the simulations, and then when we come around like 0.4, the synchronization measure R somehow increase. So if R is 1, system is fully synchronized. If R is 0, so system is not synchronized, in synchrony. And then when we are around 0.4, then our synchronization measure R is increasing and then crossing up to some coherence level. And from here, if I get the data and then if I basically plot, you see the synchronization effect. And we are now, I'm now showing you some results from this cat brain and from, I guess, cat brain, and from this synchronization happens in really the rich cloud region. So specifically, we can measure the synchronization analytically at that region. All right, so this is quite nice. So predicting like this bifurcation and so on is planned. But of course, we mathematicians in general problem is the following. We find some results and then we think that we do neuroscience, and then afterwards we go and talk to neuroscientists and then they find whatever you have done is a toy model, not really realistic. You're just basically putting equations from there to there and so on and so on. For me, amazing result. So I worked a lot on this, but neuroscientist came and then said a very wise thing. This was that how can you measure the neural activity inside the brain? So it's impossible. So like tons of neurons and so on. So how are you going to needle probe all the data? Which is impossible. of course, we didn't say, we didn't say, okay, we did a mistake and then we stop here. So we just wanted to improve our work towards that direction. And we say, like, if we have like EEG data, we go and then put these sensors. Then afterwards, these sensors are basically measuring some mean field from these neurons. And maybe instead of dealing with this problem where we have access to every neurons, maybe we can try to do reconstruction. For this mean field measured time series. So just to relax the problem, we will turn back to continuous phase equations. This is basically Chromoto model. Probably you know what's that, phase dynamics. And we have, if this part of the equation basically belongs to one of these clusters, Kate cluster, so let's say this red one, and then here these guys, they are all to all coupled, they are talking to each other, and then the mu is the coupling strength inside, and is the system side inside. And then if I assume that, so there are some connections between these mean field parts, and I have now 4 clusters, and then these clusters are connected with some network structure, and the rest is again Chromoto model. And then if this cluster is connected to that cluster, everyone is talking to everyone. So super simple model. Equation-wise, like super big, but at the end of the day, idea is simple. So you can, why we do this? Because we want to apply mean field theory as much as we can, then we can simply reduce the problem into a dealable shape. So we basically check the mean fields, then everywhere we can do mean field approximation. Actually, they are exact, as everyone is talking to everyone. And we can write the system with Chromoto order parameter. And if we do this after applying Antonsen ansatz, which is basically some changes in the form with an ansatz, then our equation become into this form, like zk equals f of z plus coupling term between these clusters. Here z, of course, now complex number, right? So since we start phases, and f again here becomes, so if you start from here and then you basically go to complex plane, so this f for sure becomes into like hop normal form. So basically it's like a phase rotations, right? So, and then if there is synchronization, you can assume that everyone is rotating together. If you counter-rotate the system, then this point will be basically, all the oscillators will be stopping at some single point. And when the synchronization is lost, then they will be again start rotating. This is somehow hop bifurcation, right? So we are basically using the hop normal form for this f. This is basically automatically coming from the this form, just basically changing the coordinates to the polar coordinates. And this is basically the coupling. See, exactly the more or less exactly. Okay, we basically studied the discrete form of this equation in the first part, and then now I'm just basically trying to say I'm not changing the things. At the end of the day, I can reach my original equations after doing some transformations. All right, let us do one example now. So here, my equation I showed you, and then this f is, as I told you, the normal form of hop bifurcation. And this A is the network structure, and then H becomes into this kind of pairwise coupling. So these are complex conjugates, this bars. And I need to choose some parameters for internal frequencies. Here I do choose some resonance satisfying conditions, which means like the sum of these two guys should equal more or less to omega 2 and then omega 4. So then there will be some resonant satisfying conditions. Why we choose these ones in that way, I will show you in a bit. So since I want to come to some conclusions, because of that reason I'm picking my numbers accordingly like this. But these like 1, 2.5 and so on is not important. Only the important thing, this should satisfy these conditions between frequencies, natural frequencies. All right, so what we do the simulate. We basically simulate the system, and this is real part of this z, and then this is imaginary part of z. So on coordinate, they are just basically rotating. If there is no coupling, we expect to see perfect circle. Because of this interactions, circles are a little bit tilted. Yeah? But still, the average radius r can be computed from Hopf normal form. Why I say this? As you see again, the coupling is small, so they are not really diverging from the original. If I unwrap these phases, then we will see in this scale only linear growth, but one can, so if I unwrap this thing, so you can see in this form, and then from here you can go and then get the phases. And then if you do have the phases, now what we want to do, just basically check out who is connected to whom. We are looking for the network topology again. So again, we came into this linear form as in the first problem, and then now we would like to apply reconstruction using again same basis pursuit idea. So here are my derivatives. Here are the candidate functions. Since according to my assumptions, I also do not know what is my H coupling function, right? So I know there is like a linear growth. This linear growth will come from this guy. This is the constant. And the rest, interactions, should be coming from some functions. As we are in polar coordinates, best candidates are trigonometric functions, sine and cosine. And then I put like many of them in a row. Then I do apply the regression, and then I get this kind of results. So these are the constants, and then this constant simply say this guy and then this guy taking these functions, and then these functions basically producing results in this phases that we collect, the mean phases of the clusters. Then when we see the reconstructed equation from this nice linear thing, then it becomes in this shape. But in the beginning, so we had only pairwise interactions, and then okay, this linear growth is there is no problem, but the interactions are not pairwise anymore. Then now we have like triplets, so higher order interactions. And the question was, where did we do the mistake? So looking for the wrong thing. And then what you will do as a first thing, as I told you, so we are looking for the equations back, but there is no unique solution. We are looking for some neighborhood, right? And then if we, how can we cross-check this? We can do the following. So we can get this system. We can simulate this system with this reconstructed ones, and then we can learn these thetas, and maybe we can even define a new variable, one of them theta1 minus theta2 plus theta3, and then the other one theta1 minus theta4 plus theta3, so only two variables. Then we can basically reduce into two variables by this change. We can check from the original system, we get thetas, and then what are the new phases. And then we can also simulate this system from the same initial condition again, and then see how it looks. And when we do that, so this green one and the purple one is coming from the original system. And then these dashed ones are coming from these equations. They are fitting perfectly well, very nice. And then if you zoom in here, you see, so this purple one and then green one is basically fluctuating, like vibrating very frequently. Yeah? So super much oscillations, fast oscillations. If you go and then check this white one, you only see the envelope of the time series. So when you do this, then of course, probably you know this one better than me. The first rule in machine learning, right? So you do try to penalize things or do this basis proceed L1 regression, loss or reach, whatever you do. What you want to do, you want to choose some parameters to not overfit your system. Simply, so when we were trying to look for the sparse solution without overfitting, we found the average. Actually, then what we learn is maybe not wrong, but we can only get the first averaging of the system. And then this idea is trying to find. Here says someone's talking to me, but I don't know from viewers. But at the end of the day, I mean, so like you just basically get data, original data, everything works perfectly fine. And as our technique is looking for a sparse recovery, then we thought these equations might be found by averaging theorems or maybe some normal forms. And this is the original one, this is the reconstructed hypernetwork, and then we want to understand why this is happening. So now, sparse recovery we did. Let us look at the sparse solution of this problem. And in general dynamical systems, the simplest form of a class of dynamical systems is given with this normal form theory. And then what you do this, you basically take the system, then afterwards you apply a coordinate transformation near identity. So which means this is small, that's why we choose always alpha small. And then if we do that, then afterwards we will have some monomials everywhere, right? So since due to this polynomial coordinate transformation, so we will have lots of terms, and afterwards we will check which terms are the resonant terms and which ones are the non-resonant, and the non-resonant ones will be chopped, then only the effective ones will be there. I don't know, maybe if we are not aware of these details, maybe you can consider this like PCA analysis. You just basically try to get the dominant ones. When you do that, then you see all the pairwise equation, pairwise functions coming from the coupling, since it was pairwise, right, in the original. And then if you do the coordinate transformation, all these pairwise things coming from this term, coupling term, are chopped. So it's gone. Perfect. So we only have like the higher order terms from the coupling. This is very good. But you cannot do these transformations only one part of the equation, right? So you have to do it to everywhere. And then when you do that, of course, some new pairwise things are appearing. So then what you need to do, then you need to apply another coordinate transformation. When you do this coordinate transformation second time, then you get here, then you also get rid of all the pairwise terms coming from the isolated dynamics, and only the higher dimensional, higher order terms are with us. So this is basically very similar to what we have seen in our reconstruction. So this is a combinatorial problem, so which is not very easy. So you need to find out which ones are resonant, which ones are not resonant. Because of that reason, we improved. We actually basically put forward one special bracket, and then if you basically put the guys together there, this bracket simply selects which ones are the resonant terms, which ones are not resonant ones. And probably you remember, I mean, so we were selecting these omega values, so two of them, if we basically linearly add, so sum two of them, then we will reach one of these frequencies. So this is basically creating the resonance. So that's why I selected this omega i's according. And then if I do this, this is the algorithm. So if network looks this type, then you just basically take it as a resonant term. If it is basically there in this shape, for instance, this is non-resonant anymore, so the summation is not equal, then you say this is non-resonant term and then you chop it. Then if you find some other resonant terms, but if this is not in the network, you again chop it. So we do have like three types of terms, and then this bracket simply filters out these things as algorithmically. And then we also share it somehow how to find these resonant and non-resonant terms with this bracket on some repository. So if you're interested, you can go and check. All right. So, and when we apply this, then afterwards, the normal form gave us exactly what we have found from the reconstruction. Then this network structure, why it's coming from sparse recovery, somehow understood by us, since we are simply finding the average of this time average. I mean, so like if you basically have a rolling window on this time series, and then if you basically get the averaging of this each window and then put them together, so this is basically kind of first averaging of the system, which is equivalent with the normal form. Perfect. So then mystery is somehow resolved here, and I showed these results in Siam meeting 2 years back, or 4 years back, I guess. And then Istvan Kiss, but other Istvan Kiss, not your colleague Istvan Kiss, chemist Istvan somehow came and then told me, you know what, I can create a very nice experiment for this thing. Then I'm not really lab person, so probably I can break down everything. So I never been there, and then I didn't see how he is doing. But he did something super amazing. He's very smart, and then we gave him like all the equations and then everything. He somehow introduced some delay feedback mechanism, and then this basically create this imaginary points of the equations that we have in the data. And then afterwards he produced some data, then on this ring topology, exactly the same topology, and we basically started to play with these potentials. And then from these potentials we compute the derivatives, since this is our setting, and we needed to do a little bit smooth it down. So when you smooth it down, so basically you lose the real part of the system, real equations of the system anyways, because you go immediately to some averaging, which is basically getting closer to the normal form that we showed. And then if we do the reconstruction, we got exactly the same result as in the theoretical part, simulation. All right, just one interesting thing that I want to show, and then if you have exactly the same equations, and then if you basically keep the coupling in this form, like quadratic, multiplicative, which means there is no really diffusive thing, so there is no like attraction of these oscillators to each other. But in this case, when you basically check the equations mathematically, you don't expect any synchronization because they are repelling each other. But then, if you do the reconstruction, then you see, actually surprisingly, this kind of repelling structures can give you this kind of reconstructions. And then if you look at it very carefully, then this is kind of master-slave system. Driver-driven system, so people do not like this master-slave anymore, I guess. So, and then driver part is 1, 2, and then driven part is 4, 3. So such cases, phase entrainment, so can happen. We know this from our like waves lectures, right? So oscillation lecture. So if this is the case, probably we can find like critical transitions to synchronization, even in this coupling term, like repelling term. And when we do the simulations, we really realized synchronization and non-synchronization in the parameter space, and we could really find out the how do you call it, like theoretically the transition point, bifurcation point. This is basically Arnold tongue for this phase entrainment. All right, so if I wrap it up, so if the networks are like heterogeneous and so on, and then if you can simply classify your nodes like a low degree node or hubs and so on, you can really estimate local dynamics, coupling, effective coupling, let's say. And if you basically remove all those things from the original data, you can get clusters, and then this is very general result. And then in part 2, so this higher order interactions, like they are really based on attraction nowadays, so we are very interested in. And we use higher order interactions in general to design things, like model things, because it really makes sense. If this is like a chemical reaction, for instance, 3-4 chemicals basically, like, or elements, whatever you call, so like basically they get together and so on. If you want to show them with a network, you have to have higher order interactions. Otherwise, you cannot model it. But actually, these higher order interactions, not only for modeling things, they can be really simplifying your complex problems into some normal forms. And then you can, like using this representation, you can find out like critical transitions normally maybe you cannot do from your original system. So this is good simplification, good reduction actually. And so in this case, then everyone should understand like hyperparameters are actually typical, they're everywhere because of nonlinear interactions that we shown here. So we have to be happy with hyperparameters. So, and please come and then see our like other colleagues' talks nowadays, like in this Beyond the Edge seminars and so on. Hopefully you are following. And then super important and interesting things are going on in higher order interaction research in network and dynamics field. All right, I guess I took a lot of time of yours. Thank you very much for having me again. If you have some questions, I'm happy.
So, you have questions, anyone? Online, if you have any questions, put them in the chat, we can filter them out.
Yes, please.
Hi, I'm Jan. Nice to meet you. Usually you start from details and then you reach at the end of the question session, the very broad one. I will start from
very
broad
you
one.
wish. Yeah.
The last comment you gave, you said, interestingly, higher order interactions are relevant as a simplification tool in a sense, right?
Yes.
And usually the biggest attack you get when you talk about this is actually that you're complexifying a potentially simpler problem.
Exactly. Yeah.
with a maybe complex dynamical system on top. So could you expand a bit on this and how, I mean,
yeah, sure.
how the two things
So
are
actually,
related?
simplifying is the following. So normal form does not mean like the sparsest solution, sparsest form of a dynamical system, but it is like simplified, right? And then normally like many dynamical systems, many systems, if they are in the same class, they do have identical normal form. And to find these normal forms, there is like a traditional way of doing this coordinate transformation. And then for our problem, and when you apply this coordinate transformation near identity, so which is basically averaging, and then instead of having like this many terms interacting between each other, like instead of 4 links, then you find only 2 hyperlinks together. And then when you have like this 4 guys together, so you have like fluctuating dynamics, and then when you simplify it to higher order interactions, for us actually, so they are not really complex or simple and so on. They are just basic functions, and then like the representation of the form is sparser. So normal forms simply do this for us, and this function simply first averaging of our regular pairwise interactions. So I don't know. I don't think we are trying to complexify or just simplifying it, and then this hyper edges appearing naturally, so without doing any specific thing. I hope clearly. I don't know.
Yeah.
Yeah.
Beside the ring graph topology, did you try any other?
Yeah, so tons of them. So here, so this 2022 paper together with Deniz and Istvan Tiago and then Jorge. So we put like many examples, many toy examples in the supplementary. So, but I do not have them here now, so on my presentation. But if you want, like we can talk about them later.
Thanks.
But you can find many examples. I mean, even what you can do is the following. So there is like, if you go to the paper and then you will find some code repository link. And then if you go there, you can basically put your own network and then your own numbers. And then if there is a normal form of it in the form, it will basically, it will draw the picture of it.
Wow.
Yeah.
Okay. I'll check.
Yeah. I mean, we can run a Python code and then see together if you want it. So it's quite simple. Yeah. And this one is not really simulating actually online we will find. So this is basically applying this bracket approach. You just basically give the network frequencies, and then this bracket basically will find out what kind of hyper network will appear again. Yes, please.
So you started with like the cat brain and
Oh, yeah.
brain and reconstructing like a brain dynamics. And have you looked at like other type of like dynamical networks and reconstructing them? Do you see, and if you have like, are they
Yeah.
similar?
This is good, yeah. I mean, actually, we have, I mean, if you're asking if we tried this on some real data, yes, we did. So I should have many other slides around. If I can see some, here. So this is also another real world experiment. So this is optoelectronic lasers. This is from Raj Roy from Maryland, I guess. Yes, so I forgot his affiliation. And then Joe Hart and so on, so they did together. And this is basically optoelectronic lasers. They published the data in 2019. We took their data. I mean, they shared data with us. Then this kind of network structure they have. And then we applied exactly the same thing. And if you basically have like just correlation of the oscillators, you find something like this. But if you go and then apply our technique and then do the reconstruction, as you see, you can do a perfect reconstruction with, again, two wrong connections. This is also another real world thing. So in the cat brain one, so the network was real, but we put some synthetic data on it. Here, everything is from lab. But apart from that, of course, so we have really tons of simulation networks. So if I can find some others for you, just to convince you. Oh, you see, for instance, Drosophila. So we found the statistical property of the network, the degree distribution, and then in the synthetic networks, we basically randomly generated scale-free graphs with some different decay parameter, power law exponent, and this is basically the real ones. These are the estimated ones. I believe we are quite accurate. Yeah. On an identity line. Yes, please.
Maybe regarding the first part, I missed a bit what are the assumptions, like what kind of features your data or your system need to have.
Okay.
To be able to, yeah.
Yeah, very good. So, like, if we have no idea about like G, F, and then H, then the main assumption, the network has to be heterogeneous. Otherwise, you cannot classify which guys are low degree nodes, which guys are hop nodes. So there is like a numerical trick, and then if the network structured in this way, and then if you have the data, you can classify what nodes are in the set of low degree ones, and then what nodes are hop ones. So if you do this classification, then afterwards you can do more or less everything. The theory here, the theory shows, works. Actually, I do not want to say works. Theory is proven under these assumptions. This F has to be C2 expanding map. And then this H has to be smooth enough because we need to take like a couple of derivatives to prove the result. And these hub nodes, they have to be very well connected to the rest of the system. What is like an expanding map? You know, so like this doubling map, triplet maps, and so on. These kind of maps are not important, but like this kind of maps are like expanding maps. And then with these ones, we can use ergodic theory very nicely, and then we can prove this rigorous without any problem. But the interesting thing is the following. Here, I say this is proven like that, but I'm using here neural dynamics, right? So this might be confusing. And then this is Rukov map. We did all the proofs, everything with doubling map and so on, expanding ones. Then afterwards we did the reconstruction. Everything worked perfectly fine. Automatically we were very happy. But afterwards we want to test with some other dynamics that we didn't prove. And whatever we tried, like differential equations, different type of dynamics and so on, theory works, but we couldn't prove yet, so very hard problem. I mean, so for general dynamics, we could only prove it for expanding maps. Okay. But when you apply numerically, it works perfectly everywhere. Generally.
And about dynamical correlations in the
Dynamical correlations means the correlations between like pairs, or?
Yeah, I mean, it's not clear. Because you just have access to the node level dynamics.
Yes.
You try to infer the full structure and the coupling.
Yes.
So
effective coupling, yeah.
Yeah. If the original one has strong correlation between.
Then okay. So if alpha is strong, like if it's not a weak coupling, then you lose the, okay, probably in applications everything will work again, but in theory not, because you somehow break down the ergodicity. So if alpha is right, so you basically change the distribution according, if you increase the alpha. So the distribution should be somehow consistent everywhere, so otherwise you cannot apply theorem. So you cannot prove if alpha is large, but probably in practical cases will work.
Yeah, this was more like my question. Beside what you can actually prove, what
exactly.
is the limit to actually be able to say this works quite well?
Exactly. For rigorous proofs, sinusoid, we do have a lot of assumptions and so on, but in practice, sinusoid works everywhere. And then I can show you that here, for instance, we do not have any loading with nodes, and then we do not have any model. So, but here, I believe, so to sort this problem out, as far as I remember, we used the F from the authors of this paper. So we didn't estimate what is f. We just basically took the f from them, since there is no way to find low degree neuronal hubs here. So because of that reason, we couldn't find directly f from this data. But if f is given, we could reconstruct the original network. In practice, I mean, so we do have some limitations, but yeah. In theory, we do have some limitations, but practice, probably we can sort out. Oh yeah.
So maybe this will be a very ignorant question, so I apologize in advance, but so for example, in EEG, fMRI and so on, you always have the issue of using the fully connected, the low correlations, or a lot of labs, they approach to have some structure, thresholding, and so on. Do you think that the way that your method works would be like a natural way of thresholding these networks?
I believe if you do the correlation or similarity analysis directly between these pairs, it will never work. I don't think this functional network approaches are fully correct in the literature. It can be correct if the coupling strength is large and if the oscillators are not in fully chaotic dynamics. If it is the case, if in this case, like so if we have like very strong chaotic units around, and then if the coupling is weak, so we know it from like the Reconstructing theorems for a long time, the decay of correlation will be exponential, so it's impossible to find any similarity between these units. But if you basically have like the mean fields and so on, probably these systems are not as correct as we expect, or maybe when you do the mean field, then system becomes into more periodic, because even in chaos, the trajectories could be dense and periodic, right? So because of the reason, maybe you can approach, but I don't know, depending on your end. But no, this is a very good question actually, so I like such a thing. But if you find what is f, and then if you basically remove everything, and if you are only left with the fluctuations, which is basically the perturbation from the other guys, then the correlation will definitely work, because you just basically remove the chaos from the system. You only have the interactions. In the interaction part, you don't have chaos. Right? Very nice. So that's why in general, so people they take it and afterwards remove the seasonalities. I mean, so we do a lot of techniques in dynamical systems and data science. They are actually dependent on this dynamics. Yeah, but at the end of the day, I mean, so like people basically take, then afterwards find the seasonalities, remove the seasonalities, get smooth the equation and so on. So I believe they are all kind of.
Because one of the issues with this kind of data is precisely the noise of the frequencies.
Sure, yeah, that's why I'm just trying to show this. If the noise is dominating, like which means if the noise is super large, like with respect, I mean, so when you compare it with the fluctuations and the noise, if they are competing, impossible to solve the problem at all. So this is of course big limitation. And now I'm working with some real data actually for some long time. It's really a nightmare actually. So, I mean, playing with the equations is fine, but yeah, so if the real data is not coming from lab, from really direct measurements, yeah, not easy job. Yeah, so I do not call myself like neuroscientist or so on. So we just basically play with the equations and then try to fit it into some interesting applications. So like you can consider my work like a toy.
Okay, thank you so much for
Thank you very much.
this really interesting presentation and the great questions. It was great to have you here. I'll just stop the recording now.
All right.